Guys, so what we are going to focus on in this lecture is the Chem 107 exam prep. Basically, some of the things you are expected to come across. Now, these are not exam questions directly. This is what you should prepare for. Are you getting it? Like what you should be expecting to see. Not that you will see exact questions with what is here. So it's better you understand each and every step I am going to be taking in this lecture in order for you to perform very well. Now, you did experiment on titrations basically this semester, right? Basically this semester you did experiment on titration. So the question is, what is titration? Right from secondary school, everybody knows what titration is. Are you getting it? You have been doing titration, but you don't really know what titration is all about. Now, titration is a quantitative analytical technique. Emphasis on quantitative because you are trying to know amount. All right? Titration is a quantitative analytical technique used to determine the concentration of an unknown solution by reacting it with a solution of known concentration. The concentration of unknown solution you are looking for is the analyte, while the one of known concentration is the titrant. You should take note. The one you are looking for is the analyte, while the one that you are using to look for another is the titrant. In most cases, the one in the burette, titration, they usually have what we call burette reading. The one in the burette is usually your titrant, while the one in your conical flask is usually your analyte. Now, this is in most cases, although it can be substituted or it could be changed. Do you understand? So what is the general idea on titration? Titration is like you are using what you know to determine what you don't know. That is what titration is all about. You are using what you know to determine what you don't know. The one that you know is the what? Titrant. The one that you don't know is the what? Analyte. Using the known to determine the unknown. Now, let me give you an example. For instance, let us say you have 5 cups of beans. Let me use this illustration. And then you have unknown cups of rice. Unknown cups of rice. Now, the 5 cup of beans is the titrant. That is the one you know. While the unknown cup of rice, you don't know how many cups of rice is there, is the analyte. Is that okay? That is the analyte. Now, my dear student, now listen. You know that, okay, here there are 5 cups of beans, but you don't know how many cups of rice are there. But let us assume you have a situation where you know that for every 1 cup of beans, you are going to cook 1 cup of rice. For every 1 cup of beans you are cooking, you will cook 1 cup of rice also. Now, let us assume you cook the first cup of beans, combine it with 1 cup of rice. You cook the second cup of beans, combine it with another cup of rice. By the time you went for the 3rd cup of beans, you discover that, oh, we still have 2 cups of beans remaining, but all the rice have finished. Are you getting it now? Like, you measure the 3rd cup of rice, all the rice are finished. Now, what information does that give to you? It tells you that normally there were 3 cups of rice that were present there, because you know that for every 1 cup of beans you prepared, you use how many cups of rice? 1 cup of rice. So for 3 cups of beans that you've prepared so far, it automatically means that you also used 3 cups of rice. That is how you use what you know to determine unknown. Now let us assume that you have unknown cup of rice also. Another illustration. Let us say for every 1 cup of beans you prepare, you use 2 cups of rice. You don't know the amount of rice there, but you know that for every 1 cup of beans you prepared, you are using 2 cups of rice. Now, in that case, let's assume you prepare 1 cup of beans. It means 1 cup from this 5 cups, you use 2 cups here. If you take another 2 cups from here, it means total you'll be using 4 cups here. If you took 3 cups from here, it means you'll be using how many cups? 6. If you took 4 cups from here, It means you'll be using how many cup? Let's say 8. You now discover that, oh, all the rice have finished, but we still have 1 cup of beans left. Are you getting it? That automatically tell you that what we have here initially were what? 8 cups of rice. So by using the beans to now compare, you should be able to now know how much of what is there unknown, how much of the unknown is present. Is that okay? So that is what titration is all about. You are comparing two things. One, you know the concentration. The titrant, you know the concentration of the titrant is known, but the analyte, you don't know the concentration. Is that okay? You don't know the concentration of the analyte, but you know the concentration of the titrant. By ratio, you are now going to confirm. Let us say you use 2 mole of the titrant, and the ratio is 1:1. If you use 2 mole of the titrant to react, it means there were 2 mole of the analyte present in a situation where the mole ratio is 1:1. Is that okay? So that is the general idea on titration. You guys are going to get titration, especially those in pharmacy, very well when you get to 200 level. But for now, let's just run through what we have here. Now, the key point is the reaction must be fast. All titration reaction must be fast. It must be complete and stoichiometric. That means there must be a relationship. For instance, what is the stoichiometric relationship between sodium hydroxide and HCl aqueous? The stoichiometric relationship, my dear student, is what? This one will give us sodium chloride plus what? Water, H2O, liquid. This is aqueous. All right? The stoichiometric relationship, the relationship between the sodium hydroxide and the HCl, that is the mole ratio. In this case, stoichiometrically, this is 1:1. Are you getting it now? So all titration experiment must be fast, the reaction must come to completion, and it should be stoichiometric. Please take note. What did we say? It must be fast, it must complete, and it must be stoichiometric. Are you getting it now? So that is that. Now, let's define some things. These are things that we've defined before. The titrant. The solution of known concentration is the titrant, the one usually in the burette. That burette reading you take in the experiment, when you say initial burette reading, final burette reading, is the titrant. That one, you know the concentration. The analyte, the solution of unknown concentration, usually in the conical flask. The burette. What is a burette? A precision glass instrument used to deliver the titrant in variable volumes or immeasurable volumes. That is what a burette is. A precision glass instrument is precise. If you want to put 1 mil, it will give you exactly 1 mil. Is that okay? A burette is a precision glass instrument. It's glass in nature, of course. You know the burette, the one that you put open small. It has a stop cock that you can tighten to stop some liquid from going in or from the analyte from, not the analyte, the titrant from going into the analyte. Are you getting it? To deliver the titrant in measurable volume. So what is in the burette is the titrant. Now, pipette used to measure and transfer a precise amount of analyte. For pipette, it will only measure a precise amount of the what? Analyte. So you pipette the analyte into a conical flask. You don't use your mouth to pipette. Please take note. It's one of the this thing you should take note of. One of the laboratory safety conditions you should take note of. You don't use your mouth to pipette. So pipette will measure and transfer a precise amount, volume of the analyte. So it's also a precision instrument. But burette can deliver variable volumes, like different volumes. While pipette, the volume of pipette is fixed. Pipette has just one calibration. Look at it. Most pipettes are usually like this. You know what a pipette is now? Long. Me, I can draw for state. It has just one this thing. If this is a 10 mil pipette, this 10 mil pipette can only deliver 10 mil. Is that okay? If this is a 10 mil pipette, this 10 mil pipette can only deliver how many mil, my dear student? 10 mil. It cannot deliver 5 mil. That's what we are trying to say, that it can measure and transfer a precise amount of the analyte, not the titrant, of the analyte. While the burette can deliver variable amount, but the volume is precise. Can deliver 10 mil, can deliver 5 mil, can deliver 2 mil, and so on and so forth. Is that okay? So take note of that. Now, indicator. What is an indicator? An indicator is a substance that changes color at or near the endpoint. That is what is usually used to know whether a titration has come to an end or we should stop the entire process or not. Use one indicator. All right? We have different indicators, right? Exactly, which we are going to look at later. The endpoints. The point in the titration where the indicator changes color is the end point. The point in the titration, you know, when you are doing your titration, you now see a particular point where that indicator you should put, maybe it was red, it now changed to pink or different colors. That is the end point. Is that okay? That is the end point. Now, what of the equivalent point? The equivalent point is different from the end point. The equivalent point is theoretical point where the amount of the titrant added is exactly stoichiometrically equal to the amount of analyte present. Now, what do I mean by that? The equivalent point is the end point where when you calculate normally, your analyte and your titrant they are stoichiometrically equal. That means the amount of analyte and the amount of titrant are stoichiometrically equal. That is the equivalent point. While the end point is where the indicator changes color. So end point is measured experimentally. That means based on the experiment, that is when you get the end point. While the equivalent point is calculated just theoretically. It's calculated theoretically. Let me state it again. The end point. Now that point when we say that your indicator when you put methyl red, methyl orange, phenolphthalein also changes color. Now at that point, we assume that the analyte and the what is it called? The analyte and the titrant have reacted, have completely reacted. Are you getting it now? Why the equivalent point is the true point that you calculated, that at this point it's supposed to have reacted, or the reaction must have come to completion at this exact point. But it's quite different from the endpoint, because endpoint are the one when experiment tell you. Equivalent point are the one we say you just calculate normal, say okay, now by this particular point, you go use do it, you go use the reaction go take come to an end. Let's take it this way. The equivalent point is just like the point at which you calculate normal, say now yeah, this reaction will take come to an end, like the titrant go don react with the analyte. Is that okay? Why the end point is the one that you now get from the experiment. Gone. Is that okay? So that is the differences between them. Now, what is standardization? Titration is standardization. Standardization is the process of determining the exact concentration of a titrant solution. It's called standardization. It is the process of determining the exact concentration of a titrant solution. What do we mean by that? What did we say concerning the titrant? We say the titrant is that solution whose concentration is accurately known. Are you getting it? That solution of known concentration is the titrant. The process of you knowing that true concentration is called standardization. Let me take it again. We say standardization is the process whereby the concentration of the titrant is accurately known. The process of knowing that, okay, this is the exact concentration of this titrant is standardization. Why we say the titrant is the solution of known concentration. How you think know that concentration is the what? Standardization. Do you get the idea now? Exactly. So that is that for standardization. Now, why is standardization necessary? Because many of these titrants, like sodium hydroxide or HCl, are difficult to obtain in pure, stable, or can absorb moisture from air. You say that property is called hygroscopy. Now, therefore, we must first prepare an approximate solution and then standardize it against what we call a primary standard. Now, what do we mean by this? Listen. you won't use sodium hydroxide as your titrant. Are you getting it? Or HCl. Either of these, sodium hydroxide. Most of the experiments people did is either use sodium hydroxide or HCl as your titrant. Now, normally, it should be known that what? The concentration of this sodium hydroxide should be accurately known for it to be used as a titrant, and the concentration of this HCl should also be accurately known for it to be used as a titrant. However, listen, this sodium hydroxide or HCl is very difficult for you to get the pure form of it. When you talk about pure form of it, it means a situation where there is no impurity. When we say, say if you measure 1 gram, that 1 gram na 1 gram. If you measure 2 gram, that 2 gram is 2 gram. But this ones here, sodium hydroxide and HCl, na lie. It's very difficult for you to get them in this pure form of 1 gram, 2 gram. So there are situations where you measure normally 2 gram, but what was actually present there is like 1.85 gram. Why? Because there are little impurities. So if you use this 1.85 gram test of, at the end of the day, that thing now, the concentration is not accurately known, because the accurate concentration is 1.85, but when you measure, you got na 2 gram you put for mind say you don't measure. But when you check detail, you discover say na 1.85 gram na in the inside. Let me take it again. This thing when you get here, sodium hydroxide, HCl, it is expected that they are pure. It is expected that the amount you measured is accurately correct. Why? Because they are the titrant. We say the titrant, you know exact concentration of the titrant. Is that understood? Now, what we are now trying to tell you is that most times it is difficult for you to obtain this sodium hydroxide and this HCl in their pure form, in such a way that for your mind, you measure 2 gram. For your mind though, but you know say now 1.85 gram now actually there inside. Why? Because of small impurities when they. So if you measure 2 gram and then what you really they say now 1.85 gram, it means you don't know the exact amount when they there in the first place. Are you getting it now? So the process of us trying to determine that what we have here is 1.85 gram and not 2 gram, so that when we are working, we know that we are working with 1.85 gram, is called standardization. Is that okay now? It's called what? Standardization. It's more like person give you, let's say, ATM give you, Nigeria ATM, okay, person count money give you, person, you go POS, go withdraw 20k, person count the money give you. You know say that person fit make mistake, especially when the money na like 200 naira or 500, person can easily make mistake. When they give you the 20k, the process of you counting that 20k to ensure say wetin really dey there na 20k is called what? Standardization. Do you get it now? Person give you 20k, you wan collect the 20k take give another person. You counting that 20k to ensure say, hey, wetin this person give me na 20k and not 19,500 is called standardization. Why? Because you know say the person when count that 20k give you, if he make mistake, actually give you 19,500 instead of 20k. Do you get it? Same thing we are having here. We are saying that sodium hydroxide and HCl must be pure, but sometimes due to impurity, due to the fact that they can go into different forms, due to the fact that they can absorb moisture from, if they absorb moisture for air, it means if maybe you weigh 2 grams, wetin dey there na 1.5, the other na water moisture na make am dey up to 2 grams. Are you getting the idea now? So the general idea is we now standardize to know, okay, this one we say na 2 grams actually dey here, but when we standardize now only 1.85 now actually dey there. That process is called standardization. And what is used to standardize it is what we call a primary standard. What we use for the standardization is called a primary standard. It's called, my dear students, a primary standard. Is that okay? Now, types of titration. Now, we have different types of titrations. 4 basic types of titration. We have acid-base titration. Please take note of it. We have precipitation titration. Here number 2. Complexometric titration. And then Redox titration. All right. That one I know right what the heck? I know right But we have three types of titration. And that one I'm important details even the important details in that particular one. Hi. Oh, what the heck? All right. Let's look at the type of titration. Acid-base titration, the first one. Now, reaction between an acid and a base to form salt and water. Acid-base titration is also called neutralization reaction. And it involves a reaction between an acid and a base, like sodium hydroxide plus, ACl plus sodium hydroxide to form sodium chloride plus water. Is that okay? HCl is the acid, sodium hydroxide is the base, sodium chloride is the salt, and what? Water. Now, it could be a strong acid, like this case. This case here is a strong acid, or it could be a weak acid, like acetic acid. This is a weak acid. You know the difference between strong acid and weak acid, right? We say strong acid, and the one we say they dissociate completely in water, it ionizes completely in water. Why weak acid is the one that does not dissociate completely in water. What we mean is that only a little will dissociate from ion. The other ones will remain in solution as the complete molecule. Is that okay? So what we are trying to say, acid-base titration, that one is the most common one. It involves reaction between an acid and a base to form salt and water. Example, you are determining the concentration of acetic acid in vinegar. Vinegar contains about 9% acetic acid also. So it's a range, 9% acetic acid. So if they give you vinegar and you want to know how much of acetic acid is present, you use acid-base titration, because acetic acid is what is present in vinegar. So you now use sodium hydroxide to react with the acid in vinegar, which is acetic acid. So when sodium hydroxide reacts with the acetic acid, it will now tell you the amount of acetic acid that is actually present. Now, in this case, your titrant is your standardized sodium hydroxide, standardized in the sense that you've known the exact concentration of sodium hydroxide. Then analyte is your vinegar, diluted form, which contains acetic acid. Indicator, you use phenolphthalein. Phenolphthalein is used for weak acid against strong base. Weak acid against strong base. So acid-base titration is also called neutralization reaction. Please take note. You may be asked, acid-base titration is also called what? Neutralization reaction. Is that okay? It's also called neutralization reaction. Now, the next one is Redox titration. That one contains important points, of which I didn't actually write it here. But let me see if I can. That is the second one. You see, after first, this thing jumped to third. We are supposed to have second. Now, a redox titration, let me just talk about it briefly here. A redox titration, my dear student, is a titration between a reducing agent and an oxidizing agent. That is the reason why we call it redox titration. That is the second type of titration, between reducing agent and oxidizing agent. That's redox titration. It involves electron transfer. It involves electron transfer. We say in redox reaction, when electrons are transferred, it is called oxidation. When electrons are received, it is called reduction. Electron transfer, oxidation. When you transfer electrons, somebody must receive those electrons. The one that is receiving the electron, we say is what? Reduction. Receive, reduce, reduction. Is that okay? Now, in redox titration, one of the substances oxidized. I'm trying to get information on this so that just be writing it at the corner of your note. I cannot go back and start preparing slide on that. In redox reaction, one of the species is oxidized, and one of the species is reduced. That's what happens in redox titration. Now, at equivalent point, what do you say equivalent point is? The point where the analyte and the titrant have equal amount. So at equivalent point for redox titration, the amount of the oxidizing agent and the amount of the reducing agent is equal. Now, common types of redox titration. Common types of redox titration. You have reaction of potassium permanganate with iron, determination of iron using potassium permanganate. Iron 2 plus using potassium permanganate. Now take note, they may ask you what is the color of potassium permanganate. It's a very important point. Take note of it. It's purple. Potassium permanganate is what color? Ololo, purple. Please take note of it. Potassium permanganate is what? Purple. Now, in this titration, you don't need any indicator, no indicator needed in redox titration with potassium permanganate. The reason why you don't need any indicator is because potassium permanganate is an indicator itself. It's self-indicating. It changes from purple to colorless when the reaction has come to an end. Are you getting it now? So potassium permanganate is purple in color. It is a self-indicator. No indicator is needed. Are you getting it? Then another, this is an oxidizing agent. Potassium permanganate is the oxidizing agent in this titration. Oxidizing agent. Then another oxidizing agent that is used for other titration is potassium heptazoldichromate, K2CR2O7. Now, this one often require indicator like diphenylamine. Diphenylamine. It often involves the use of this particular indicator. So please take note. Potassium permanganate is what color? Purple. One titration they use potassium permanganate. Redox titration. Redox titration involves what? Reaction between a reducing agent and what? An oxidizing agent. What is the color of potassium permanganate? Purple. In that reaction, potassium permanganate is what? An oxidizing agent. Is that okay? Does reaction involve indicator? No. Why? Because potassium permanganate is self-indicating. Self-indicating. Change from this purple color to what? Colorless. Is that okay? Self-indicating. So that is that for the second type of titration. So the ones we've discussed so far, acid-base titration, redox titration. Is that okay? The next one is precipitation titration. Now, precipitation titration is the formation of an insoluble precipitate. The insoluble precipitate that will be filtered out, and then you measure the amounts present. It's often the technique that is employed in gravimetric analysis. Now, how does it work? See how it work. It just be like the way you mix milk. You mix milk and water. When you mix milk and water, after some time, wetin go happen? If you increase the temperature, normally that milk and water go mix together. Are you getting it? But if na cold water you use, the milk go form balls on top of the water. They will not mix together that much. In such a way that if you filter, you'll be able to get the milk separate and get the water separate. Are you getting it? So the formation of something that is insoluble, like you go see, dey soluble, is the principle in precipitation titration. Like there's a precipitate. When you do white precipitate form, it means that there is something that is not dissolved in the titration experiment. That thing that is not dissolved, now you can filter it and then measure the weight present. Now, for instance, determining the chloride ion concentration in water, that is argentometry, uses this titration. The titrant in that reaction is silver nitrate. Then analyte is water sample with chloride ion. Is that okay? The indicator that is used in that situation is potassium chromate, which gives a brick red precipitate of silver chromate after all chlorine has precipitated as white HCl. Now, the general idea is that you have this silver. We say we use silver nitrate. The silver ion will react with the chloride ion in water. This is the titrant. We react with the chloride ion in water to form silver chloride. This silver chloride is a white precipitate. You will see it as white. Is that okay? So a situation where you react silver nitrate with chloride ion, the silver will react with the chlorine to form insoluble silver chloride. This insoluble silver chloride now is the one that will now form that precipitate. It's not dissolving. Is that okay? It will form a precipitate. So that is the basic idea on precipitation titration. Argentometry is an example of precipitation titration. They may give to you the determination of chloride in water is what type of titration is precipitation titration or argentometry using silver nitrate. They may ask you, silver chloride is insoluble in water. True or false? It's insoluble, not in water. It's insoluble, or insoluble silver chloride will be formed. It's true. Is that okay? So that is precipitation titration. The key thing I want you to take away is that they form insoluble precipitate. Determination of chloride ion in water sample, precipitation titration. What is used as a titrant? Silver nitrate. All right? And it will form insoluble silver chloride, white in color. Then the next one is complexometric titration, my dear student. Now, complexometric titration leads to the formation of soluble complex ion called chelating. You usually use what we call chelating agent. It forms soluble complex ion. They are soluble. Now, for instance, determination of water hardness. You know, water hardness adds concentration of calcium ion and magnesium ion. These are the things that causes either permanent hardness or temporary hardness of water. The titrant that is usually used in complexometric titration is EDTA, which is called ethylene diamine tetraacetate. It's a polydentate ligand. It's called polydentate ligand. Most of you will not really understand what we mean by polydentate ligand. And it is also a chelating agent, like I said, that is usually used chelating agent. All right. The indicator that is used in that case is eriochrome black tea. So in complexometric titration, what is the titrant often used? EDTA, ethylene diamine tetraacetate. All right. The indicator used is what? Eriochrome black tea. It is blue in free solution and white red when complexed with calcium or magnesium ion. So it means when the complex have been formed, it changes from blue, eriochrome black tea changes from blue to wine red. All right. So reaction between metals like calcium and magnesium and EDTA is to form a metal EDTA complex is what we call complexometric titration. You guys are going to learn this, those in chemistry, under coordination chemistry, coordination compounds rather. Coordination compounds. But the general idea I want you to know is EDTA, when you hear of EDTA, ethylene diamine tetraacetate, know that you're talking about complexometric titration. Are you getting it? Eriochrome black tea, complexometric titration. Determination of water hardness or concentration of calcium ion and magnesium ion in water. What do you use? Complexometric titration. Then determination of chloride in water using silver nitrate, precipitation titration. Then determination of ion, right? Ion is what? Redox titration. Using potassium permanganate, redox titration. Then, of course, we have our acid-base titration. So basically, what are the types of titration I've listed? Acid-base titration, redox titration, then precipitation titration, and what? Complexometric titration. These are the various types of titration you should take cognizance of. Now, the next thing we are going to